Good day. The second part of Chapter 8 focuses on the counting rules in Section 8.4 in your textbook. So you can go to page 198, please. If you look at the outcomes in the study guide, you should be able to first of all apply the multiplication rule, and we use the multiplication rule to determine the number of possible outcomes in an experiment without actually listing the different outcomes, like we did with a tree diagram in the previous section. Then, secondly, you should be able to do calculations regarding permutations, and then lastly, do calculations regarding combinations. It's important that you are able to distinguish between permutations and combinations. With permutations, we have an ordered set of objects or people, and we can draw people or objects with or without replacement, but the order or the rank in which the people or items are drawn is important. For example, if you choose a PIN code for your cell phone, 123 and 321 will be different from each other. So the order in which the numbers are chosen are important. Then for combinations, we have an unordered set of objects or people where order is not important, and we only do combinations without replacement. So for example, if you draw a lotto ball, that's an example of a combination. The multiplication rule is also known as the basic counting rule, and it's applicable to multi-stage experiments. So let's say you have different actions, and each of these actions can be then carried out in a certain number of ways. So you will have a certain number of outcomes for each action. And then you just take the product of all the number of outcomes for each action to determine the total number of outcomes or the ways in which the experiment can be carried out. For example, let's say that the first action can be carried out in M1 ways, the second action can be carried out in M2 ways, up to the kth action that can be carried out in MK ways. Okay, let's look at a practical example of this. If you toss two coins, for instance, your first coin will have two possible outcomes, heads or tails. Your second coin will also have two possible outcomes, heads or tails. So in total, you have 2 times 2 possible outcomes, which will be 4 in total. If you have 3 possible coins that you toss, your coins will also have 2 possible outcomes each time. So 2 times 2 times 2 will give you 8. So you will have 8 possible outcomes in total for that multi-stage experiment. Let's look at a couple of examples on the multiplication rule. So in this first example, I tell you, suppose you can choose a car in any of 4 brands in any of 3 colors. How many choices are there in total? So instead of drawing the tree diagram and determining your possible number of outcomes, you can just use the multiplication rule. So there's 4 brands, that's your first action. Your second action is the 3 colors, so 4 times 3 will give you 12 possible choices in total. For example, 8.7, they state, an experiment involves tossing a pair of dice and observing the numbers on the upper faces. Find the number of individual outcomes in a sample space for this experiment. So if you look at your first die, you will have 6 possible outcomes because you can have 1, 2, 3, 4, 5 up to 6 on that die. And then for the second die, you will also have 6 possible outcomes. So in total, you will have 6 times 6, which will be 36 possible outcomes in total. In example 8.8, they did an experiment where they randomly selected 20 people and they recorded their birthday. They tell you that they ignored leap years and that each of the people had 365 distinct birthdays. So that means that there's 365 possible days for each person to celebrate his or her birthday. And then they want you to find the total number of outcomes in the sample space. Okay, so the first person has 365 possible days that he can celebrate his birthday. The same for the second person up to the 20th person. So we will multiply that for 20 times. So in short, your total number of outcomes in the sample space will then be 365 to the power 20. The second part of the question, they assume that all the outcomes have an equal chance of occurring, and they want to know the probability that each person of the 20 has a different birthday. In part 1, we said this is the formula for calculating the probability of an event A. Now, in part A of the question, we already calculated the number of outcomes in our sample space. So now we just need to define event A and determine the number of outcomes in event A. So event A can be defined as each person has a different birthday. Then the first person will have 365 possible birthdays, but then for the second person, the birthday must be different than the first person, so the second person will only have 364 possible days in which he can have his birthday. Then the third person will have 363 possible days in which he can have his birthday, because it must be different from all the others. So every time you subtract 1, so up to the 20th person, which will have then 346 possible days in which he can have his birthday. Okay, and that will then be our number of outcomes in A. We have our number of outcomes in the sample space, so our probability that A will occur will be 0.589. Your turn. You can try class exercise 1, please. Okay, if we look at the answer, I tell you that you have 2 choices for starters each time. You have 4 options for the main course each time, and you have 3 choices for dessert each time. So I want to know for A, how many different meals can be chosen. So we can apply the multiplication rule there. So you will have 2 times 4 times 3 choices each time. So it will give you a total of 24. And for B, how many different meals contain meat dishes? Okay, our starters will stay the same. Our mains will be influenced by this because vegetarian lasagna will be excluded since it doesn't contain meat. But our options for our desserts will stay the same. So now if we apply the multiplication rule, our total number of options will be 2 times 3 times 3, which will be 18 choices in total. The official definition of a permutation is given on page 200, and a permutation is an ordered arrangement of a number of objects. So if I have R objects, then the total number of arrangements of those R objects will be R factorial. So if you think back to mathematics, factorial tells you it's the product of all the positive integer values less than or equal to that value. So if you have 4 factorial, for instance, it will be 4 times 3 times 2 times 1. So let's look at an example. In example 8.9, they tell you, in how many ways can the letters A, B, and C be arranged? So R is going to be equal to 3 letters. So I will have 3 factorial, or then 6 ways to arrange the letters. Since I have 3 possible letters for the first position, 2 possible letters in the second position, and then 1 possible letter in the third position, and these will then be the arrangements of those 3 letters. Okay, but suppose now that we have n objects in total and we only want to draw R objects from those n objects without replacement, and we want to determine in how many ways that can be done. There's a formula in the textbook that you can use, and we read it as n permutation R, or you can use this formula, or great news, there's a shortcut function on your calculator. So you can locate it in permutation R. If you look at the Casio, it is located above the multiplication sign, And for the Sharp calculator, it's above the digit 6. Okay, so let's look at an example of how to practice that on the calculator. So I tell you there's 10 horses in a race, and we want to determine in how many ways can the top 3 places be determined. So I will have 10 permutation 3. So you input 10, you locate your function, and then you place 3. So on the Casio, you will input 10, then you press shift, and then you locate your function above the multiplication sign, and then you press 3, and then equals to, so you will have 720 permutations in total. Or for the Sharp calculator, you will input 10, then you press second function, you locate your function above the digit 6, then you enter 3, and then you press equals to, and you will also have 720 permutations. If you struggled with following that, please ask the class assistants to help you. The keywords to look out for in these type of permutation sums is an ordered arrangement, or then if rank is involved in the question. For example, in example 8.10, they tell you how many arrangements are possible if we need to arrange 2 letters from the letters A, B, C, and D. So we have 4 letters in total, that will be my N, and we have 2 letters that we want to select. So I will have R equal to 2, so 4 permutation 2 will then give us 12. You can do that on your calculator then, or use the formula, or you can say 4 times 3 will be 12, because you have 4 possible letters in the first position, and then 3 possible letters for the second position. In the following example, they tell you, for the selection of a committee, there are 5 male candidates for 2 vacancies. In how many possible ways can a chairman and a secretary be elected? So I have different positions, a chairman and a secretary, so there's rank involved. So this will also be a permutation without replacement. I have 5 candidates that I can select the 2 vacancies from. So my N will be 5 and my R will be 2. So we want to determine then 5 permutation 2, which will give us 20 possible ways in which they can be selected. Or if you understand this formula better, you have 5 possible candidates for the first position, and then 4 for the second position. So you will have 20 ways to select the people in total. In example 8.12, they want you to determine in how many ways can a Blue Bulls rugby team schedule 3 games if all competing teams are willing to play the matches on any of 5 dates. This is going to be a permutation without replacement, and your keyword here was schedule, because that means that there will be a certain order involved, and you can't have games on more than 1 date, so it's without replacement. So my N is going to be 5, since I have 5 dates in total, and my R is going to be 3 games then. So we want to determine 5 permutation 3, so we will have 60 possible ways in total. Or you can see it this way, you have 5 possible dates for the first game, 4 possible dates for the second game, and 3 possible dates for the third game, so you will have 60 possible ways in total. In example 8.13, they tell you the names of 3 employees are to be randomly drawn without replacement from a bowl containing the names of 30 employees of a small company. The person whose name is drawn first receives 1,000 Rand, and the individuals whose names are drawn second and third receives 500 Rand and 200 Rand respectively. How many individual outcomes are associated with this experiment? Okay, so this is going to be a permutation without replacement, since there's rank involved for the different amounts, and the first prize can't be given to the second person as well, etc. So my N is going to be 30 in total, and I draw 3 employees. So we are going to determine 30 permutation 3, so it will give us 24,360 possible outcomes in total. Or then, if you understand this formula better, you can use that as well. Your turn. You can try class exercise 2, please. Okay, let's look at the solution. There are 12 contestants in the race. How many different ways can the first, second and third place be arranged? There is rank involved because it's first, second and third place, so it's a permutation, and it's going to be without replacement because the same contestant can't take the first and the second place, for example. Then we have 12 in total, and there's 3 top spots. So N is going to be 12, R is going to be 3. So 12 permutation 3 will give us 1,320. Or you could have used this formula and you would get the same number of ways. For permutations with replacement, you also have n possible objects to choose from every time, and you want to choose R objects as well, but every time you have n possibilities to choose from. So the number of permutations will be n to the power R. For example, for a PIN code for your cell phone, there's 10 possible digits that you can choose from. So you can choose 10 each time, and however many you want to choose. Let's say you want a 4 PIN code, then it will be 10 to the power 4. Okay, here's another example for you. Here I tell you, you have to choose a new code for your security system. The code consists of 3 digits, and digits may be repeated. So that means it will be with replacement. And how many possible security codes are there? Well, the order of the codes are important, so it will be a permutation. And like I said, it can be repeated, so it will be with replacement. And you will have 10 digits to choose from each time. You can choose any digits from 0 up to 9. So it will be 10 possibilities for the first digit, 10 for the second digit, and also 10 possibilities for the third digit. So we have 10,000 possible security codes in total, or you could have said 10 to the power 3 will be 1,000. For combinations, you also have a total of n objects, and you only want to draw R objects from those n objects, but now the order is not important, and we only do combinations without replacement, and the notation that we use to indicate that is this or this one, and it's read as n combination R. Please note that for this notation, it's not n divided by R. That's a function. It's n combination R. On the calculator, you're welcome to use the shortcut then you don't have to use this formula. So for the Casio calculator, that function is located above the division sign, and for the Sharp calculator, it's above the digit 5. So let's quickly practice how to do combinations on the calculator. So in this example, I tell you, you have 10 balls in a bag, and you want to draw 3 balls from those 10 balls. So we want to determine 10 combination 3 then. So on the Casio calculator, you will input 10, you will press shift, you will locate n combination R above the division sign, then you press 3 and you press equals to, so we will have 120 combinations in total. On the Sharp calculator, you will input 10, press second function, get the function above the digit 5, enter 3 and press equals to, so you will also have 120 combinations in total. Let's look at a couple of examples. On example 8.14, I tell you, there are 5 qualified applicants for 2 editorial positions at a university newspaper. 2 of these applicants are men and 3 women. If the positions are filled by randomly selecting 2 of the 5 applicants, what is the probability that neither of the men are selected? Okay, this is going to be a combination first of all, because there's 2 editorial positions. So it's the same position, so the rank or order in which the applicants are chosen is not important. They ask you for a probability. So we are going to use combinations to determine the number of outcomes in event A and the number of outcomes in your sample space. So if we look at the sample space, first of all, that's the easiest place to start. They tell you that they will select 2 from 5 applicants. So that's my total. So N is going to be 5, R is going to be 2. So we want to determine N combination R, so 5 combination 2, and that will give us 10 outcomes in total. We can define event A then as the event that 2 women are selected, so no men will be selected. We are going to have 2 combinations for the number of women that was drawn and for the number of men that was drawn. So we can use the multiplication rule to determine the number of outcomes in event A. So if you look at the first combination, that is the number of ways the women can be selected. So we have 3 women in total and we select 2 women for that. So 3 combination 2, and then for the men there's 2 men, but we didn't select any of the men, so we have 2 combination 0. So the total number of ways in which the women can be selected is 3. So our probability will be 3 over 10. So we have a probability of 0.3. Just a note on the combinations above the line and below the line. In your denominator and your numerator, the number that you can select from must be the same as the number that you selected. So if you look on the previous slide on the number of outcomes in your sample space, it was 5 combination 2. That was below the line then. So above the line we should have the same amount. So that should add up for the 2 combinations to 5. And here at the bottom this should add up to 2. In the next example they tell you the Dean's Office has received 12 nominations from which to designate 4 student representatives to serve on campus curriculum committee. Among the nominees, 5 are third-year mathematics students and 7 are third-year statistics students. Suppose 4 students are selected randomly from the group of 12 to serve on the committee. What is the probability of the event that 3 mathematics students and 1 statistics students are selected? Okay, we have a probability that we want to determine again. So we need to determine the number of outcomes in event A and the number of outcomes in our sample space. Let's start with our sample space again. So we want to select 4 students from a possible number of 12 students. So our number of outcomes in our sample space will be 12 combination 4, which will be 495. Then we can define event A as the event that 3 mathematics students and 1 statistics student are selected. So we are going to have 2 combinations again. A combination for the mathematics students and a combination for the statistics students are collected. So if we apply the multiplication rule, the number of outcomes in event A will be 5 combination 3 for the mathematics students and 7 combination 1 for the statistics students. So we will have a total number of outcomes of 70 in event A. So our probability will be 70 over 495, which will be 0.141. Then just to come back to the note I mentioned earlier, now you can see here, that's a total of 12. a total of 12 over here if you add that. That will be a total of 4, so you have a total of 4 there. So your combinations above the line and below the line should be the same. In the last class example, what is the probability that you will win the lotto? Well, first of all, will this be a combination or a permutation? It's a combination because the order in which the 6 balls are chosen from the 49 is not important, and it's done without replacement because you choose a ball and then you do not replace it again. So in our probability, we need to determine the number of outcomes in our sample space again and in our event A. So in the sample space, you will have 49 combination 6 because you have a total of 49, your N, and you choose 6 balls from there, your R. Then on top, for your number of outcomes in event A, you will use the multiplication rule again because you have 2 combinations. Your combination for choosing the winning balls will be 6 combination 6, and your combination for choosing the incorrect balls will be 43 combination 0. So your chance of winning the lotto will be almost 1 in 14 million. So I don't think any of us are going to be winning the lotto anytime soon, unfortunately. For the exercises on part 2, you can complete exercise 6 for me, please.